Alright, this lesson is about implicit differentiation. So this is going to clean up some of the scraps from what we talked about earlier. So the important thing here is to note that what we have done up to this point, we have almost been spoiled, right? Is we've talked about how to develop all of the derivative rules from this specific form where y is a function of x. And this here we call explicit form, because what we're doing is we're isolating y on one side and saying that y is dependent on x. And so if we have y on one side, then we can develop all these rules for dy dx, right, the rate of change. So this lesson is going to do something very different. So we're going to talk about things that might look like this, right? So the form is very different here. And you'll notice in cases like this, it may not be practical, feasible, or even possible to solve for y. So in this case, if we could solve for y, then we could go back and use these basic rules that we developed. But if we can't solve for y, and we still want to find dy dx, or the derivative, then that's really what this lesson is all about, finding the derivative when your function or relationship is provided in this kind of form. So this form that we have here, this is what we call implicit form, because it is not in this form where y is isolated on one side, and so we're going to develop the tools to talk about how to do this. So the basic assumption here, all we're going to assume, and this is pretty straightforward, to be able to differentiate something like this, is even if we're not able to isolate y on one side, we're going to assume that in theory that y depends on x. Right? So you can see that what we're saying here is very similar to this explicit form. So we're going to assume that y depends on x, and that y is a function of x. So with this, you can see that if you have any variation of y, if you have something like, I'll write a couple of things down, if you encounter something like the square root of y or the tangent of y, right, then there's more than meets the eye here, because this is a square root function, but it depends on x. And this is a tangent function, but this also depends on x. So what has definitely come to play in this lesson is the chain rule, because this function here is actually something that depends on x, so this is acting like an inside function. So when you encounter derivatives of functions like this, you really have to use the chain rule. So what I'd like to do to start things rolling is to do a mini problem, right? I want to do something like, how do we find the derivative of y cubed, right, if we're making this assumption that y really depends on x. So we're going to go through that example. Okay, and what I'll do as a reminder, I'll just keep this up here, because this is the basic assumption in this lesson. Okay, so let's walk through the details here. So we're going to run through and say, what is the derivative, right, with respect to x of y cubed? So the first assumption is we're depending that y really depends on x. So we can write that down so we can see it. So this is what that looks like. And so the moment you see this, this is going to remind us of an inside function like u of x. So the way we would differentiate this is by the general power rule. Okay, so the way we go about this is we would write 3, and then we would drop the power by 1, but we're going to keep the inside function, right, y of x. And then we chase that by looking at the derivative here and differentiating the inside. Right, so it looks like this. So once you understand this, the dependency on x, what we tend to do is we simplify the notation. So you don't have to write y of x, but you could just write y. And if you do that here, you can express it this way. So really the derivative of y cubed is very similar to the derivative of x cubed, right? So you could see the derivative of y cubed is 3y squared, but you have this dy dx here. So if we just remind ourselves, we could write this down. Okay, so this is the old familiar one that we know. So the derivative of x cubed is 3x squared, but notice the derivative of y cubed is in a very similar way, right, is 3y squared. So it has a very similar structure here. The fundamental difference is that y depends on x, so we have to multiply by the derivative of the inner part. And in this case, that's y of x, so we multiply it by dy dx. And this is more or less what the section looks like, right? When you encounter a function of y, you really have to use the chain rule, so that's the most important piece that we're talking about here. So this can be seen in a variety of different problems. I'll just slap another one right up here so you can see it, right? So this top derivative we talked about a couple of lessons ago. It's very familiar. So when you find the derivative of sine of x, you get the cosine of x. So if you use this assumption here, if you have to differentiate the sine of y, we're going to treat y as a function of x. So the derivative of the sine of y is cosine of y, very similar, but y is dependent on x, so you multiply by y prime or dy dx. So this pattern that you see here is the same thing that you can see right here. So that's basically all there is to implicit differentiation. And so what I'd like to close with is, let's go back to that first thing that we talked about, right? Where you might not want to isolate for y, or it might not even be possible, right, to get y alone on one side. And so let's go through all the mechanics here and see if we can find dy dx. Okay, so we're going to run through this problem, and we're just going to leave the problem in its exact state, right? We're not going to move anything around, and we're going to differentiate both sides. So I'll show this step in detail. So this is a step, once you get pretty good at this, you could probably just think about it mentally, and you don't have to write it down. So we're going to differentiate the left and differentiate the right, and this is both with respect to x. So now on this side, when you find the derivative of y squared, right, this is going to give us 2y to the first power, and then as we just saw, right, you have to differentiate the inside function. So you're going to have a dy dx there, or a y prime. So as we move to this side, the derivative of sine is cosine. So we have the cosine of x plus y, and then we have to use the chain rule. So we have to go inside here and then differentiate this inner function. So we're going to multiply by this derivative. So these are added, so you can do them separately. The derivative of x is 1, and then the derivative of y is dy dx, y prime. So this first step is where all the calculus occurs. And then what we might want to do here is to just solve for y prime, and then that'll be the solution to the problem. So you'll notice there's a y prime here and also a y prime there. So what you want to probably do is to isolate them on one side and then just solve for it. So I'll see if I can simplify this. Okay, so this cosine is one big term. We're going to take this and distribute it through. All right, we're going to bring it through. So this will be cosine x plus y. And then we'll add to it the same thing, cosine x plus y. And then we'll have y prime. Okay, and I'll continue the work up above. So we'll notice here that what we could probably do is to take this term and to bring it over to the left-hand side, because then that way we'll have all the y prime terms on one side of the equation. So this will be 2y, y prime, and then we're going to subtract this. So minus cosine of x plus y, y prime, and that will equal just this term here. Okay, so this is where we sit here. And then what you can see is you can factor out a y prime. So the rest of the problem here is going to be algebra. So hopefully I can fit it here. So I'm going to remove a y prime. I'm going to factor that out. So it'll be 2y minus this cosine term. How's that look? And then we still have this cosine term, like so. And then if you want your derivative, dy dx, you simply divide by this term in parentheses. So cosine term here, and then it appears we have 2y minus the cosine, x plus y. So we'll highlight this here. And that would be our answer. So going back and looking at what we had, okay, so this was the original problem to find the derivative of this function, right? The slope of the tangent line at any point on the curve. And the big thing is we're using this assumption, right? That's the most important thing, that even if we don't have y expressed as a function of x, in theory that's what it is. So you can tell your answer here is different than in previous sections because the derivative here you could see is entirely dependent on x's and y's. And this is very typical of getting the solutions in this section, is that because you're not bothering to solve for y in the beginning, you can expect to see y in your final answer. So dy dx here is given by this expression, and the key again is just treating y as a function of x and using the chain rule.